In this problem, we are given a tank in the shape of a circular cylinder that is 4 meters in diameter, 8 meters long, and is lying on its side. The tank is partially filled with some liquid such that the depth of the liquid in the tank is 1 meter. Our task is to find the volume of the liquid inside the tank. To accomplish this task, we will use the method of parallel plane sections. The method of parallel plane sections calls for using parallel planes for slicing the volume just as some of us would slice a loaf of bread. The slicing planes can be in any direction as long as they are all parallel. For this problem, we will slice up the volume in 2 different ways. First, we use horizontal planes or planes that coincide with or are parallel to the surface of the liquid in the tank. The horizontal cross-sections, if not for their faces that lie on the lateral side of the tank, would look like planks of wood or rectangular parallelepipeds, where each face of the plank is at right angles with the other faces that it intersects. Next, we use vertical planes or planes perpendicular to the central axis of the tank to slice up the volume. The result are these half-moon-like cross-sections that are identical in shape and in area. Using the horizontal sections that resemble rectangular parallelepipeds, we will indeed treat the sections as such. We ignore the curvature along the 2 curved faces of each section and so obtain an approximation for the volume of each section. Eventually, we will apply a limit process to arrive at the exact volume of the liquid. Let us suppose that we have n parallel sections. Suppose that the diagram on the right shows the ith section as viewed from one end of the tank, I going from 1 to n. The volume of a rectangular parallelepiped is equal to its length times its width times its height or thickness. Let V sub I be the volume of the ith parallelepiped. Then V sub I is equal to its length L sub I times its width W sub I times its height or thickness H sub I. The length of each section is just the length of the tank, which is 8 meters. Therefore, V sub I is equal to 8 times W sub I times H sub I. By the way, we take W sub I to be the width of the top part of the section. It is crucial with the method of parallel plane sections to determine immediately the thickness of each section. A natural choice for the thickness seems to be the height of each section. This height is along the vertical direction, and so we draw the y-axis, which we choose to drop from the center of the circular cross-section of the tank. We designate the center of the circular cross-section of the tank as y equals 0. We designate the bottom of the cross-section as y equals -2, since the tank's diameter is 2 meters. Since this is for the ith section, let the y value at the top of this section be y sub I. Let the thickness of this section be delta sub I y, which we already know to be equal to h sub I. Because the thickness is in terms of y, we must also express w sub I in terms of y. The distance of the center of the circular cross-section to the top of the ith section is the absolute value of y sub I. We need the absolute value here since y sub I is negative. The radius of the cross-section is 2. This right side here has length w sub I over 2. And now we apply the Pythagorean theorem. And so w sub I over 2 quantity squared plus y sub I squared equals 2 squared. Solving for w sub I, we get that w sub I equals the square root of 16 minus 4 y sub I squared. And so we have v sub I equals 8 times w sub I, which is equal to the square root of 16 minus 4 y sub I squared, times h sub I, which is delta sub I y. Now this is the approximate volume of just the ith section out of n sections. Therefore, the volume of the liquid in the tank is approximated by the sum from I equals 1 to n of 8 times the square root of 16 minus 4 y sub I squared times delta sub I y. As the maximum thickness of all the sections tends to 0, this Riemann sum should tend towards a definite integral. Therefore, the volume of the liquid in the tank is exactly equal to the integral from the lower limit of y equals minus 2 to the upper limit of y equals minus 1 on the surface of the liquid of 8 times the square root of 16 minus 4y squared. We leave it as an integration exercise for the viewer to check that the volume of the liquid in the tank is 32 pi over 3 minus 8 times square root of 3 cubic meters. Now let's apply vertical cross sections to find the volume of the liquid. Since the sections are all identical from one end of the tank to the other, we use the very basic formula that the volume of the liquid in the tank is equal to the area of each cross section times the length of the tank, the length being perpendicular to each cross section. And so the volume of the liquid in the tank is 8 times the cross-sectional area A. We just need to find the area of each cross-section. To find the area of each vertical cross-section, we connect the endpoints of each section to the center of the circular cross-section of the tank. With an isosceles triangle sitting atop the vertical cross-section, we now have a pie-shaped region or sector. If we can find the central angle of this sector, then we can find the area of the sector. The sector corresponds to the central angle theta. While the entire circular end of the tank corresponds to 2 pi radians. If theta is in radians, the area of the sector divided by the area of the circle should be equal to theta divided by 2 pi. The area of the circle, of course, is pi times r squared. With r equals 2, the area of the circle is 2 squared times pi, or 4 pi. Solving for the area of the sector, we get that the area of the sector is 2 theta. Now we only need to find theta. We drop a perpendicular from the center of the circle to the surface of the liquid. This perpendicular is of unit length, since the liquid is 1 meter deep inside the tank and the tank has a radius of 2 meters. This angle must be theta over 2 since we have an isosceles triangle and the perpendicular bisects the isosceles triangle. Therefore, cosine theta over 2 equals 1/2, so that theta over 2 is pi over 3. And theta equals 2 pi over 3. This means the area of the sector, which is 2 theta, is 4 pi over 3 square meters. From 4 pi over 3, we subtract the area of the isosceles triangle to get the area of the vertical cross-section. Applying the Pythagorean theorem to the left half of the isosceles triangle, this side must have length square root of 3. And the base of the isosceles triangle must be 2 times the square root of 3. Hence, the area of the isosceles triangle is half the base, which is 2 times the square root of 3, times the height, which is 1. Therefore, the area of the isosceles triangle is equal to the square root of 3 square meters. And so, we subtract the area of the isosceles triangle from the area of the sector to get the area of the vertical cross-section, which we have called A. A equals 4 pi over 3 minus the square root of 3 square meters. The volume of the liquid is 8 times A. And so, multiplying A by 8, the volume of the liquid is 32 pi over 3 minus 8 times the square root of 3 cubic meters.